So, yeah, so we begin recording. So, welcome everybody. Our guest speaker is Professor Pankaj Joshi. Professor Joshi is a distinguished professor of physics and founding director of the International Center for Space and Cosmology at Ahmedabad University, India. So his today's lecture is about changing paradigms in black hole physics. Please, Pankaj, begin your talk.
Okay, thank you very much. Can you hear me?
Yeah, at least
Thank
I can
you.
hear you.
Okay, thank you. I would like to warmly thank all the organizing institutions, as well as all the friends.
You're welcome.
Our discussion and the dialogue today is the changing paradigms in black hole physics. There have been several major important developments in the black hole physics taking place over past a few decades. When we look out there in the universe with the kind of major missions that we have uh, nowadays, such as, for example, the square kilometer array, the 30 TMT LIGO. You see, some of these are coming up, but then some of the missions such as the Event Horizon Telescope, Space Telescope, these are, for example, very much in operation. And when we see the universe, we see a whole lot of galaxies. This is, of course, as you are aware, another uh, instrument or the space mission, the Chandra Observatory, which is much more relevant to the black holes, is really the X-ray observatory. Here are the galaxies that we see, and the remarkable point is each of these galaxies contains some 400 to 500 billions of stars. This is, of course, another galaxy, such as this one. Now, one of the most important key issues in astrophysics and cosmology today, and in the black hole physics itself, is what happens when a massive star dies. The story really goes back all the way to Professor Chandrasekhar, Subramaniam Chandrasekhar's work. He gave his theory on star collapse and stable configuration limits, and pointed out, in fact, that this is the an extract from his paper in 1935 itself. He says that when a star is, you see, a small mass like that of the sun, then it must stabilize after, you see, ejecting its outer envelopes. But a star of large mass, uh, by this he meant, you see, those beyond the Chandrasekhar limit, they cannot pass to the white dwarf stage. And one is left speculating on other possibilities. So, you see, this is the intriguing sentence. What happens to large mass stars when they run out of their nuclear fuels? This is just a pictorial description. A sun is as small as, shown by the arrow on your left-hand side. And then there are big enough stars such as the Sirius, the Pollux, the Arcturus, and so on. And the point is, while the sun has lived some 500, you see, the life of the sun is about 10 billion years, and while it has lived some 5 billion years, it has the life left another 5 billion years. But if the stars are much more massive than sun, say 10 solar mass, 20 solar mass, then they burn much, much faster. And the question of final fate of massive stars is then coming up, because the stars which are some 10, 20, 30 solar masses, they will burn up within a matter of, 20, 30, 40 millions, a few millions of years. And what happens to such stars? Now, while discussing this question, we are facing really the general theory of relativity. Einstein gravity has given numerous very interesting implications, such as black holes, the Big Bang. Most recently, we are discussing gravitational waves, the multiverses, even time warps, and space-time singularities, naked singularities. These are all very much under the discussion as implications of Einstein theory. Now, the important point here is the beginning by the Oppenheimer and Snyder, as well as Datt in 1938. They studied basically the gravitational collapse of a massive star, the Oppenheimer-Snyder work. Okay, let me just go. Right. See, this was their basic picture. They evolved the star in space and time, and the outcome really was a space-time singularity. Now, the full structure of this space-time became clear much, much later. But in 1939 paper itself, in fact, Oppenheimer and Snyder alluded to what is called an invisible star. They were referring to the very high redshift surface, which then came to be known as the event horizon later on. But you see, in that year itself, really, Einstein himself wrote a paper saying that, well, a star cannot undergo this kind of indefinite continual collapse, and this is not so physically realistic picture. And you see, Einstein has spoken, and then the subject was quiet. In any case, it was the heyday of quantum mechanics, and a lot of developments were taking place. However, in 1960s, really, there was a resurgence of interest in this particular work of Oppenheimer, Snyder, and Datt. And why? That was because of the discovery of quasars, and you see the jets from the centers of galaxies, radio galaxies, so on and so forth. Now, so much of energy was being radiated in this particular objects that no known processes were really able to explain this kind of enormous energy outputs by this astrophysical, or the you see the objects like quasars in the faraway space. And that is where really uh, uh, the interest revived in the work of uh, Oppenheimer and Snyder. People just said that, you see, there was this paper where the continual collapse was studied, and some very interesting outcomes were pointed out. The picture that emerged, as I showed you before a moment, was that this is the kind of picture that Oppenheimer and Snyder really came up with. The star collapses, an invisible surface develops, and then at the center, there is a space-time singularity. Now, there is a region here, as I said, the surface of infinite redshift. So below that surface, no signal will really come out at all. And this is came to be known, it came to be realized that a particular region forms in space and time from which no particles or not even the light will come out. And then this has the structure that is seen here on the right hand side at the center. There is a singularity, and then there is event horizon, and then there is also something called a photon sphere. We will refer to that a little later. And then you see the artist's depiction is also given that there is a region in the space and time, which is a black hole. Now, this calculation was in a way somewhat simplistic, the Oppenheimer-Snyder calculation. They had assumed that the density is constant throughout the interior of the star, that is from center to the boundary. Then the matter has no pressure, there is no rotation, there is spherical symmetry, so on and so forth. They had to do all this because the Einstein equations are so difficult to really solve. And then when these objects, quasars and so on were discovered, then there was this question, as I said, that what is the source of all this energy? And people thought that this exotic objects that were discovered, those could have a potential to generate so much more of the energies. And then it was assumed that all stars, whether they are spherical or not so spherical, whether they have pressure inside, whether the densities are, you see, not uniform, it was assumed that they all collapse to the same kind of generic behavior which was seen in the Oppenheimer and Snyder picture. That is, they collapse to black hole and hiding the final space-time singularity. So, assuming this, then in 70s and later 60s, huge developments took place in the physics and astrophysics of the black holes. The well-known names are Hawking, Stephen Hawking, Roger Penrose, John Wheeler, so on and so forth. So the typical paradigm that came into being is you have a stellar nebula, you have average star, then it goes to a red giant and planetary nebula, and finally, you see there is a white dwarf. On the other hand, you have stellar nebula, and the star is, you see, well massive, that is 10, 20, 30 solar masses. In that case, what you have is a red supergiant. You have a supernova possibly for 8 to 10 solar mass stars. And then the final outcome will be if the star is up to 7 or 8 solar masses, you will have a neutron star. But if it is much more massive than that, then you will have a black hole. So the first paradigm shift happened, after the Oppenheimer-Snyder paper, the Einstein work. The subject was quiet, but the subject was revived, as I said, in the later 60s and 70s in an extensive manner. And what really happened was that, as I pointed out to you, the key problem was unresolved. The assumption was made that all massive stars must typically collapse the same Oppenheimer-Snyder Datt way. But then you know that in science, either theoretically you have to prove or observationally you have to verify. So the question really remained open and it has been termed, for example, Jim Hartle, when I discussed with him and also in his report to the US Academy of Sciences, named this as one of the foremost, most important question open in astrophysics and cosmology. This academy frontier reports are available. In fact, the point is that the real stars are not necessarily homogeneous in the sense that the density is higher at the center, slowly tapering off when you move from the center to the boundary. They have not vanishing pressures within, they have internal pressures as opposed to the idealized model of the uh, Oppenheimer and Snyder. Uh, Now, in 80s and later years, this big problem that what really happens to the gravitational collapse of massive stars when you take more realistic assumptions, this was analyzed quite extensively. I will go only into brief details and refer to some references later on. But so much activity went on. People analyzed several and many gravitational collapse models of massive collapsing matter clouds within the framework of Einstein theory of general relativity. The conclusion that came out was depending on the internal initial data, the internal profile of the star, namely how the density is distributed, how the pressures are distributed, so on and so forth. Uh, the uh, outcome really changes. The central singularity is sometimes visible and sometimes a black hole forms. Now, let me give you an example. See, here's the brief outline: Schwarzschild, Oppenheimer, Schneider, Penrose's cosmic censorship conjecture. Uh, Now, let us take an example. Rather than taking a completely homogeneous density, let us take a density profile which is, say, higher at the center. This ρ2 term here is actually negative. So at the center, the density is ρ0. And then as you move away from the center, then the density decreases. Now, you again solve the same spherical symmetric gravitational collapse equations, which, I mean, same metric that Oppenheimer and Snyder had used. Now it becomes, you see, an inhomogeneous metric. Interestingly, this metric was given way back in 1934 by Tolman. Uh, the completely general consideration of an inhomogeneous dust collapse. Now, if you solve the equations, and work out all the details, then the structure of the event horizons and the apparent horizon is, very typical. What is, you see, written below is the equation for the apparent horizon. I'll show you the picture in a moment, but this f naught term comes from the integration of the, first equation, the density profile. This f naught is called a mass function. The key point that I would like to make is look at the third term, which is Fn. So when you have ρ2 R square present, that is the inhomogeneity is present, in that case, then the third term actually dominates because it has the power 2 as compared to the R cubed density profile. And then as a result, what happens is something very interesting. The apparent horizon, which was, you see earlier in the earlier picture, in this picture that you see here, the apparent horizon, if you see from the singularity, you see, if you see it, it is decreasing away from the singularity as you go to the boundary of the star, you see, because the singularity is forming later, so it is decreasing away and when it reaches the boundary and then of course the event horizon has started forming, which meets the apparent horizon at the boundary. Now, as opposed to that, because of the equations that I showed you just now, the apparent horizon now, in the case of the inhomogeneous density profile, it has an increasing profile from the center. Now you can see that the apparent horizon is increasing, and the very interesting outcome of such a phenomenon, that is the entire causal structure changing, is that there is a whole family of outgoing null geodesics emerging from the singularity. So singularity is no longer hidden completely within the black hole region here. But now you have the null geodesics or even the time-like geodesics emerging from the singularity. Now, what I have done here, I have done nothing illegal here. No phantom fields, no, you see, ghost fields, nothing, no additional assumptions. I have taken, in fact, an astrophysically realistic assumption, namely that the density of the star is higher at the center and then decreasing away from the center, and then you get a qualitative change, uh, namely that the first point of the singularity becomes visible here. Uh, in fact, then, as I was telling you just before a moment, many more general models were discussed by my group and our students, our collaborators, and also internationally, many other groups in Italy, Japan. You see Giulio Magli, Kenichi Nakao, Harada, and others, and also in US some other groups. Detailed discussions were carried out on gravitational models, and we obtained a generic expression for the apparent horizon. Look at this very interesting expression of apparent horizon. You have certain term chi naught, and that chi naught in the upper equation is obtained in the, you see, from the initial data and evolutions in the correlates. Basic thing I want to tell you is that depending on what the internal profiles are, the apparent horizon behavior is determined, and it is the behavior of the apparent horizon that decides whether you will have a black hole or a naked singularity. The cartoon here, you see, depicts on your left, you have the initial surface, you have initial distribution of the densities and pressures, and then depending on the evolutions subject to the energy conditions, you have either a black hole or a naked singularity emerging within the space. The right-hand side graphics show you the distribution of black holes and naked singularities for a typical mass and you see energy profiles. And the darker region is naked singularity, the upper region is black hole. You can see that both of them are occurring generically as the outcome of a collapse. The discussions then went on, the theoretical research went on. You see, as I will mention in a matter of a few minutes, uh, an important theme that we investigated was that rather than causing a continual collapse, can we create equilibrium configurations also, or can we have you see time-like naked singularities also? Can we examine a scalar field collapse also, and non-zero potentials which are so important in early universe and so on. And some of these works involve Dipanjan Day and Kaushiki, and also especially the strength of the singularity, because if it is singularity is not sufficiently strong, in that case, uh, then it may not be a genuine singularity. It might be a weaker singularity. And in that case, you see, if the singularity is weaker that way, then it may not be a genuine singularity. Uh, so the point is that uh, this was examined by Karim Mosani, Kaushiki, and Jai Trivedi and Tapo, Banja, and so on. So all these works have been going on. Uh, there are two important things here. Sometimes the rays can come out, but then they, you see, fall inside to the singularity. That is the left-hand picture. The other is the globally visible singularity where the rays will go away. This is just, a list of various things that have been examined, numerical models, the gravitational waves, the spherical collapse with non-spherical perturbations, and so on and so forth. The point is that depending on initial data, the naked singularities will develop as collapse final states, and then at other times, the black holes will develop. And uh, this development has very intriguing theoretical as well as observational consequences. You see, I showed you the earlier paradigm picture, how what will happen when a massive star collapses. You see, white dwarf or neutron star or black hole. But now we seem to have the outcome out of all these theoretical discussions that if you have featherweight stars, then you have white dwarfs. If you have 8 to 10 solar masses of stars, then you have a neutron star. And then if you have heavyweight stars, then either black hole or exploding fireball, uh, which is a naked singularity. Huge discussions, you see, because lot of black hole physics, black hole thermodynamics, the laws of event horizon, increase entropy, all these things assumed what is called the cosmic censorship, namely that all massive stars must collapse to a black hole only. But at some stage, Stephen Hawking admitted, accepted that yes, in fact, naked singularities can develop out of gravitational collapse. So this is it became the first page article in the New York Times. And then, of course, we have had the Nobel Prize announcement in 2020, Roger Penrose, Genzel, and Gaze. Genzel and Gaze mainly showed that, you see, there is a very supermassive, compact, high mass object sitting at the center of our own galaxy. Sagittarius, a star. Uh, and Penrose was quoted, which I'll read out because it is amusing and intriguing, for the discovery that black hole formation is a robust prediction of the general theory of relativity. This is from the Nobel citation. However, in a recent interview that Penrose gave to New Scientist, you see, uh, he clarified.
Hello. We cannot hear anything. Can you skip perhaps this movie?
Oh, you cannot hear?
No. I
Nothing.
suggest to skip it.
Yeah, please
Oh, I
skip it.
see. Uh, next one. All right. I'll send the movie again. I think you see the key point that Penrose is saying. You see, he's correcting the Nobel Prize citation. He is saying that. Can you hear me? Hello.
Yes,
Hello.
Yes.
Okay. Okay.
Yes, sir,
Okay.
we can hear you.
Okay. Thank you. Thank you.
Yes, sir.
Yes, you see, Roger Penrose was cited as for the discovery that black hole formation is a robust prediction of the general theory of relativity. In the video, you see the link is given at the bottom. You can listen to it again. You see the YouTube link is there with the new scientist interview. There he says that I actually showed the existence of singularities and not black holes. And then he also further clarified that these singularities could be either naked singularities or they could be within the black hole. Please do listen to the video. The link is given below. So the latest development has been now there have been recent research papers from top academic places like Cambridge and Perimeter, Princeton in higher dimensional space-times and four-dimensional GR and so on. Uh, Theoretically, it looks like fairly reasonably well established that both black holes and naked singularities could be the outcome of gravitational collapse. And now Penrose also has clarified and you see suggested that either of the outcome is possible. Uh, Now, you see, astronomer friends actually straight away ask that all right, you guys do all this theory, and that is all fine. But suppose they are there in theory, that is singularities, which is very strong gravity regions in the space and time. So if they are visible, then what is the observational consequence? What are the observational and astrophysical implications? Can we distinguish them in the skies? So this is the point on which we will devote, rest of our discussion. In fact, there are many possibilities. Uh, and many investigations in past years have been carried out related to the observational consequences of the singularities if they are visible, accretion disk properties around black holes and naked singularities, high energy particle collisions and consequences, gravitational lensing around these objects, shadows of black holes and naked singularities, event horizon telescope. I will cover in the rest of my talk a few of these points. In our paper with Malafarina and Ramesh Narayan, we examined the accretion disk emissions from black holes and naked singularities. The Schwarzschild black hole case, you can see that after a certain frequency, there is a sudden fall off in the emission frequency. However, when the singularity is visible, in fact, the stable circular orbits go very close to the singularity, and as a result, then you have very high frequency radiations available. This is seen in our paper of 2014. Then there is another, very interesting, in a series of papers with Mandar Patil, I showed that there are very high energy collisions occurring in the vicinity of a naked singularity. You probably might remember this Barnard's silk, effect. So they studied particle collisions near the event horizon, and if some fine tunings are made, then very high energy collisions will take place. So we showed, in collaboration with Harada and Kimura, Nakao, Patil, and some of our collaborators, that very ultra high energy collisions will take place without fine tuning, without that much of fine tuning in the Kerr geometry, in various other geometries. We have also discussed possible energy extraction from the vicinity of, ultra strong gravitational fields. We are aware, energy extraction from Argo regions and the Kerr black hole and so on. So can we extract energy from ultra strong gravity fields near, visible singularities? So Vishwa Patel, Kaunte, Acharya Parth, Bamania, and so on, we examined this, energy extraction mechanisms. I will not go to the details, mathematical formalism of the same, but energy extraction is an extremely interesting phenomenon, such as, we have Penrose process, magnetic Penrose process, particle acceleration due to high curvature regions, Blandford-Janek, and Blandford-Pine, and collisional Penrose, so on and so forth. So this is a very fruitful, fertile arena where you can examine whether you can see the you can have the energy extraction. Now, gravitational lensing, the bending of rays. This is really at the foundation of the science of the shadows, black hole shadows, and singularity shadows. That is, happening. The array of radio telescopes, Event Horizon Telescope, and probing the very center of galaxy to get the shadow of the uh, black hole, so to say. Now, uh, this video doesn't have sound. Yes. So this is how, typically the cartoon of how a shadow forms. Now this is by the way, that previous video we have put in the chat box. So you can say it anytime you want to. You see in the year 2022 May, the shadow of the center of our galaxy was reported. Shadow of the center region of the SGR A star, which has a mass of some 4.3 million solar masses. Some inclinations, distance, diameter, all these parameters are given here, which you can look up. But the important point is that uh, they tried to match it with a static or very slowly rotating black hole, and there were some disfavors. That is, there was no complete matching of the black hole model. As a result of that, by the way, this is a work with Saurabh, where we compare the shadows created by black holes and naked singularities. But I'll come to that in a moment. The important point is that the Event Horizon Telescope papers, as referenced here, they say that you see uh, the JMN singularity, naked singularity with a photon sphere, may be one of the best possible black hole mimickers for the SGR star, and that is why the point is both the black hole, that is your extreme right, the Schwarzschild black hole, whereas the JMN model, which I mentioned earlier in the context of the accretion disk, they both in fact produce shadows, similar shadows actually. So that is why the Event Horizon Telescopes results examined. Now, one intriguing point here is finding by Ashok Joshi and the Panjan and our team, which is that uh, sometimes it is thought that you must have a photon sphere if you were to have, a shadow. But here a model was given where a photon sphere was not present and still a shadow was found. So all these investigations tell you that there is a lot more compared to arriving at simplistic, conclusions. You see, just as Penrose clarified, you see, in his Nobel Prize citation itself. So similarly, here also we have to go into various details. Here is a shadow produced by Schwarzschild, and at the right side is the shadow produced by the JMN. Even though on the face of it they look similar in size, etc., there will be very intricate intensity distribution differences in both these images. So the point is, the observations of shadow by themselves is not sufficient to determine the existence of black holes. So some of the black holes model may not exactly match also the observations. And then what do you do? What next? So the thing to do is that, you see, you need to examine further the, you see, orbits of stars around the galactic So this is one of the sort of investigations in that direction. And Parth Babania and you see us we're looking into the orbits around the JNW. This is Janus Newman Winnicourt, you see, model of a naked singularity. Uh, and it turned out interestingly that the precision is negative as opposed to the usual positive precision that we see in the usual objects. Could this be a signature of naked singularity? Well, the investigation is on, and the ball is out in the, I mean, the question is out in the open, and interesting works are sort of happening. The point is that the naked singularities with or without photon spheres can cast shadows similar to that of black holes. We need more details in order to distinguish. There are retrograde precession of time-like orbits, which are not possible in Schwarzschild or Kerr black hole, but they are possible in the naked singularity space-times. And then we also examined, some further details of orbits and so on. So the question, as the Event Horizon Telescope papers asked, that could naked singularities be possible candidates which might represent the space-time structure of the galactic center. Please, Vladimir, warn me when I have some 10 minutes or 5 minutes.
Okay, you've got still, let's say, 15 minutes, okay, but not more.
Thank you. Wonderful. Thank you. I'm in. Fine. Great. So, the point that we are making here is that the issue of black holes versus, you see, singularity, visible singularity outcome. This is fundamental to, you see, modern theory of black holes. The key paradigm change, again, I am indicating here, is that in 70s and early 80s, even when it was a sort of only the black hole picture and black hole thermodynamics and so on and so forth, later, the detailed mathematical as well as yield a very interesting difference. If I say it this way, the change in the causal structure of the occurrence of event horizons and apparent horizons. Mark these two words, event horizons, apparent horizons. How they behave, this is what really determines, you see, whether the singularity is visible or not. And then if you have the models, for example, if you have physically realistic models, that is in that case, then is the connection on?
We can't see your transparency.
Okay, very good. So I'll go on. So you see, if the singularities are, if they arise in nature, in that case,
I'm afraid you can't see your slides. Oh, now it's okay. It's okay now.
Wonderful. So you see, the point is, if the visible singularities occur, now you see we have very high energy, explosive cosmic phenomena in the universe. Could visible singularities be typical candidates? Because you see, only when you can probe closer to the singularity, then you can access the extreme energetics happening in the universe. And now there have been observations of, you see, I'll just mention to you a very fantastic gamma ray burst. So much energy, has been there. And when you have this kind of energies, then, who knows? Maybe are you probing even the quantum gravity implications? So, the point is that the point is that uh, you see, the point is that the general relativity theory is implying for us very strong gravity regions, where quantum gravity and general relativity both come into their own. So ultra strong gravity regions and quantum gravity, and now this could be visible as opposed to the black hole scenario. So as Robert Wald pointed out, if censorship fails and the singularities become visible, then in a literal sense, we would be face to face with the laws of quantum gravity. Whenever gravitational collapse to a naked singularity occurs in distant regions of our universe. Uh, I have called, you see, in my Scientific American article, this objects as even quantum stars, because sometimes you see, naked singularity becomes too technical a term. So quantum stars, that is these, objects, ultra high energy, ultra high gravity objects, if they happen in star collapse, then exciting observational implications could be there. And the question that we would ask is, can we observe and see quantum gravity effects taking place in their vicinity? Uh, uh, from the very interior, very sort of deep regions of the collapsing objects, we could have in principle emissions. We examined one toy model. You see, using the loop quantum gravity, we studied a simple scalar field collapse model. And in this particular plot, F is the mass, you see, vertical axis, and the horizontal is the radius of the star. So when you go to very small radii, that is in the very final stages of the collapse, the emission becomes, you see, very, very powerful in the upper box figure delta F by total mass. So the emission basically is the peaks, and you can have a burst like behavior due to very strong negative pressures. The P effective becomes some minus 9 times rho effective. So this paper was, I think, a 2006 Physical Review Letters paper. Uh, uh, Quantum gravity, is again a subject which requires a lot more investigation. So obviously, these are, things like mini Big Bang, actually, so to say, produced for you. Big Bang was there once and for all, which produced the universe. But then now, whenever a very massive star would collapse, you could have sort of, an explosive event. We wonder, whether the ultra powerful gamma ray bursts are that. We wrote some, tentative papers on that, but a lot more work needs to be done. The question is, does nature produce for us a quantum gravity lab, possibly when a massive star collapses? In this case, in that case, then, this becomes equally important, even for the unification, unified theories, and so on, and so forth. So typically, the astrophysical signatures, what are they? Accretion disk and shadow properties, energy extraction, relativistic orbits, as I was saying, the orbits of the stars, then, tidal disruption, lens flaring effect, gamma ray bursts, relativistic jets, all these pulsar timings, all these possibilities are there, and you sort of have to go on. Now, just the last part of my talk, you know this picture, the LIGO observatory, the two very massive objects, typically called black holes, come together, collide, and this is the typical plot of the waves. But what I want to point out to you, a very interesting sort of observation by Kip Thorne, made in his Vishweshwara lecture. He, studied this orbits, and then this is in the case of a black hole, how the orbits will look like. But then he asked a question. These are his slides, by the way, from his lecture. He asked the question, what if the central body is not a black hole? For example, a naked singularity. And then he said that the maps will be very widely different in that particular case. So what I am trying to say is even the top brains are looking at this sort of possibilities. In the panel below, if you are interested, in having more details, you might want to look up my Scientific American article, the cover story, and then which was repeated also in 2022 in their special collectors volumes. And then the story of collapsing stars is, you see, a somewhat semi-popular presentation, whereas the monographs from the Cambridge as well as the Oxford, they have been sort of giving you many more technical details. To end on a lighter note, a lawyer in America wrote this book, A Naked Singularity. Actually, it refers to the prison system in the USA. And now, just a year ago or so, even a movie has been made from this particular novel. And Julia Keller, Pulitzer Prize winner, author, wrote an article in the Chicago Tribune reviewing this book, where she quoted from my Scientific American article, what a naked singularity is. So all this is intriguing and amusing. These are, many of our collaborators. Dipanjan, Tapo, Kawarpreet, Rita, Ashok Joshi, Divyesh, Kaushiki, Jay, Rajibul, Vishwa, Kaunte, Parth, Bamania, Saurabh, and so on. We have active groups and good discussions. Thank you so much for again this opportunity of interaction, and I'm grateful to all the organizing institutions.
Thank you very much for your very interesting talk. And now we have some time for questions.
Sure, it will be my pleasure.
Some comments, remarks? I can't hear any. So let us thank the speaker.
Okay.
I thank everyone for the participation in this seminar, and we close the meeting. Goodbye. Goodbye.
Okay. Bye-bye.
Bye-bye.